In this section, I'd like to introduce the subset construction algorithm to convert an NFA to an equivalent DFA by running two examples. The first example, the NFA has no epsilon transitions, and the second one, the NFA has epsilon transitions. So, given an NFA like this, let me briefly describe this NFA. It has four states, A, B, C, D. The start state is A, and the final state is D. Remember, we can only have one single start state, but we can have many accept states. So in this machine, we only have one accept state, D. That's also okay. Start from A. If I read a 0, I can either stay at A or go to B. And if I read a 1, I will go to C. From B or C, if I read a 1, it will reach D. And from D, if I read a 1, I will stay at D. And for those missing transitions, that means if you read a symbol, it dies. For example, if you read a symbol 0 from B, that branch of computation will die. Alright, the 5 tuple for this NFA is Q, the set of states, A, B, C, D. Sigma, the alphabet, only 0 and 1, two symbols in the alphabet. And the start state is A, and the final states are D. For the transition, start from A, it can reach A and B by consuming a single 0. And it can reach C by consuming a single 1. From B, if you read a 0, it can reach empty set. That means it can reach nothing. And reading a 1, it can reach D. The same thing happens for C. Reading a 0, it dies. Reading a 1, it goes to D. And in D, if you read a 0, it dies. And if you read a 1, it stays as D. That's the NFA. Now we want to convert this NFA to a DFA. We know by definition, a DFA is an NFA. It's a special case. For NFA, the transition function takes a state to a set of states. That means starting from this state, reading this symbol, it can reach this many states. The principle to convert an NFA to a DFA is use the subset. So every state of this DFA M prime corresponds to a set of states of M. That means these sets are reachable from the start state by reading some string. If we write the states explicitly, this Q prime is going to be empty set, all the singletons, and all the sets containing 2 elements, and all the sets containing 3 elements, and the set containing all 4 elements. So there are 2 to the k many of states. In this case, M has 4 states. So in principle, we should have 2 to the 4, 16 states for this equivalent DFA. Each subset corresponds to one of the possibilities the equivalent DFA must remember. So the DFA simulating the NFA has 2 to the k states. And we say this Q prime equals the power set of Q. Remember, the power set of Q is all the subsets of Q. And the transition function is, for example, we have a state R in this DFA. R is going to be a set of states in NFA. And reading this symbol A, the resulting state is going to be a set, and each member is going to be a state in this NFA. Now we check each state in this resulting state. That is the state that can be reached from each member in this R by reading a symbol A. So when M prime reads a symbol A in state R, it shows where A can take each state in R. What we do in the computation is, for each member in this R, we check the transition in NFA and see what are the resulting states by reading this symbol A. And we do this for each member in this R, and we take the union of the result states. All right, we have specified Q and transition function delta. Now let's compute the transitions for each state in Q prime. In principle, you should do this by each state in Q prime. That means there are 2 to the k many states. But many of those states are not reachable from the start state. So the algorithm I show now is going to be start from the start state and see what we can reach, and we only compute the transitions for the reachable states. The start state of this DFA is going to be the set of states in this NFA that can be reached from the start state of this NFA without consuming any symbols. So in this case, the start state will be the set containing only that start state A in this NFA. Because by consuming nothing, I can only reach this A. All right, that's my start state. Now I need to compute the resulting states for this A by consuming a single symbol, either 0 or 1, because that's my alphabet. If I have more symbols for my alphabet, then I need to do these transitions for each symbol in my alphabet. So from A, if I read a symbol 0, I can either follow the transition on A and ends in A, or follow the transition from A to B and ends in B. So A, B are the states that can be reached from this A by reading a single symbol 0. So the resulting states will be A and B for this transition from A by reading a single symbol 0. And since that state only has A, one member, that's all. If there are more members in this state, then I need to do this for each member and get the result state after the transition and take the union of the resulting states. Now from A, by reading a single symbol 1, I can reach this C and nothing else. So the resulting states is just C. Now the states A, B, and C are new states. These states are reachable from my start state. So I put these new states into the left column. The left column are all the states that are reachable from this start state through some string. And I need to do the computation, the transitions for each of the reachable states. Now for this state AB, I need to compute the result state for A and the result state for B after consuming a single symbol 0. From A, by reading a single symbol 0, I can reach AB. And from B, by reading a single symbol 0, I reach nothing, because there's no transition from B on 0. So that's empty set. I take the union of the resulting states. That will be AB union empty set. The resulting states are A and B. Now for 1, from AB, what are the states I can reach by consuming this single symbol 1? So from A, reading a 1 leads to C, and from B, reading a 1 leads to D. So I take the union of the resulting states. That will be CD. Remember the procedure is, for each member in the left set, I compute the resulting states by consuming this single symbol. Now I have all those resulting states. I need to take the union of them. That means from AB, I can reach CD by reading a single symbol 1. Now I have 2 states, AB and CD. And I need to check if they are new states. If they are, then I put them into the left column because I need to compute the transitions for them. So only this CD is a new state. So I will put that CD into the left column. Now we go to the next state, which is C. From C, reading a single symbol 0, I reach nothing because there's no transition out of C on 0. And that's it. By reading a 1, I can reach this state D and nothing else. So the resulting states are just D. Now I have two new states, this empty state and this D. I need to add this empty set to this left column and this D to this left column. So from this empty set, I can reach nothing because I have nothing to start with. So I will reach empty set itself by reading a 0 or a 1. Now for this set CD, from C, by reading a symbol 0, I can reach nothing, empty set. And from D, reading the 0, I still reach nothing, so it's a union of nothing and nothing. The resulting states are empty set. That means from C and D, I can reach empty set. I can reach nothing by reading the symbol 0 because there's no transitions for this 0. Now for 1, from C, I can reach D by reading a 1. And from D, I can also reach D itself by reading a 1. Take the union of these two, I have D as the resulting state. Now I have two states, empty set and this D. Both of them are not new states, so I will continue the computation on the left column. I have one state D now. From D, I can reach empty set by reading a 0, and I can reach D itself by reading a 1. Now I have two states, empty set and D, and they are not new states. And I check the left column, there's no states left. So that's the end of the computation for this transition table. That means we have reached all the states that are reachable from the start states and computed their transitions on each symbol. Remember, for a DFA, for each state, there need to be the size of the alphabet number of arrows out of each state. Alright, so according to this table, we can draw the diagram. Starting from state A, reading a 0, I can reach AB. Reading a 1, I can reach C. And in AB, if I read a 0, I stay at AB. And read a 1, I reach CD. And from this C, reading a 0, I reach empty set. And read a 1, I reach that D. The special thing about this is we have an empty set. If you check that state, once you reach that state, you stay at that state. Usually, we call this kind of states as trap states. That means it's trapped. Once you are there, you stay there. You can't get out. Alright, then continuing, we need to specify the start state and the final states. The start state is simple. That's the set of states that can be reached from the start state of this NFA by consuming nothing. So in this case, the set containing a single A is the start state of this DFA. The final states can be multiple states, and each state is going to be a set. Each set contains 0 or more states in the NFA. So we check each state, each member of that set, and see if that set contains an accept state in this NFA. If it does, then it should be an accept state in this DFA. In this example, we have two accept states. One is CD and another is D. CD contains a member D, and D contains a member D. And D is an accept state in NFA. We only need to have one. If we have more, for example, if we have another state E, which is also an accept state in the NFA, then if you have both DE, that state is a final state, an accept state. If it only has D or it only has E, that's also an accept state. The meaning of this is, from the start state, I can reach this state. This state contains multiple states in the NFA. That means consuming some string, I can reach these states with different branches. Remember, by doing the computation of an NFA on the string, it can have many paths, many branches. If either of the branch reaches an accept state, the machine should accept the string. If all the resulting states after consuming all the symbols in the string is a non-accept state, then the machine should reject the string. So that's the whole procedure of subset construction. It got the name subset construction because the DFA has the states being a subset of the state in NFA. This NFA we just ran has no epsilon transitions. Now let's consider another example with epsilon transitions. This machine only differs from the original one by adding an epsilon transition from B to C. We follow in a similar procedure. The only difference is the start state and the transition function. For the start state, the principle is the same. The start state of this DFA needs to be the set of states that can be reached from the start state of this NFA by consuming nothing. If you have epsilon transitions, you should consider the start state of this NFA and all the states that can be reached from the start state by consuming only epsilon transitions. And we call that the closure of a set. The closure of a set is the set of states that can be reached from each member of the set by consuming 0 or more epsilon transitions. The principle of the transition function is still I compute the resulting states of each member in the set, and I take the union of that. After that, I need to take the closure of the set. That means, starting from these resulting states, what are the states I can reach by following 0 or more epsilon transitions? Now let's run this algorithm on this machine. I start from the start state, which is A. Because there's no epsilon transitions out of A, the start state will only contain A. From A, if I read a single symbol 0, I can reach A and B. That's the result states. After I got A and B, I should take the closure of AB. The closure of AB is the set of states that can be reached from AB by consuming nothing. So from A, it can reach A itself. From B, it can reach B and C. So the closure of the result states is going to be the result. From A, reading the symbol 1, I can reach C. And then I take the closure of C. That's C, because there's no epsilon transitions out of this C. So these new states are A, B, C, and C. I put them in the left column. You always put all the new states in the left column, then do the next transition, because it's very easy to forget some states. All right, for the next state, A, B, C, by consuming a single symbol 0, from A, I can reach A and B. From B, I can reach nothing. And from C, I can reach nothing. Remember, I need to consume this symbol first, then take the closure of the result states. So in this case, from B, by consuming a symbol 0, I should reach empty set instead of C. Because I need to consume this symbol 0, then follow epsilon transitions from that. Since there's no transition from B on 0, I can reach empty set. Then I take the closure of the empty set. All right, so the result state will be AB union empty set union empty set. Then I take the closure of that. The closure of AB is going to be ABC. Because these are the states that can be reached from AB by following 0 or more epsilon transitions. Now consider that symbol 1. From ABC, I can reach C because I can read a 1 and go from A to C. And D from B and D from C. So I take the union of those, that will be C and D. After that, I take the closure of C and D. That means I need to compute the set of states that can be reached from C and D by following 0 or more epsilon transitions. If you check the machine, there is no epsilon transitions out of C and D. So the closure of C and D is C and D. Now we check the states, A, B, C, and C, D. Only C, D is a new state, so I put that C, D in the left column. That means this C, D is reachable from the start state. Now I check the next transition for C. From C, after reading the symbol 0, I can reach nothing, so it's empty set. Then I take the closure of that empty set, which is also empty set, because from nothing, you can reach nothing. And from C, by reading the symbol 1, I can reach D. Then I take the closure of D, which is also D, because there's no epsilon transitions out of D. Now check the new states. Empty set and D are both new states, so I should put those two states in the left column. From empty set, reading the symbol 1 or 0, I will reach nothing, still empty set, because from nothing, you can reach nothing. Alright, then for this state, CD. From C, I can reach nothing by reading a 0, and from D, I can reach nothing by reading a 0 because there's no transitions on 0. So the resulting states are empty set. Then I take the closure of empty set, which is empty set. Then for CD, reading the symbol 1, from C, I can reach D, and from D, I can reach D. Then I take the closure of that, which is still D. Now we check the states. We have empty set and D. They are already in the left column, so I don't need to do anything for them, and I continue with the computation for the next transition. That will be D. From D, I can reach empty set on a 0, and I can reach itself on a 1. I take the closure of the resulting states. So the only difference between this epsilon transition and the one without epsilon transition is after computing the resulting states, I need to take the closure of them. Now I draw the diagram from this computation table. The start state is A, which is the states that can be reached from the start state of this NFA by consuming nothing. In this case, it will be A itself. If there are epsilon transitions out of A, then you need to follow the epsilon transitions and see what are the states that can be reached by following only epsilon transitions. So from A, reading a 0, I reach ABC, and reading a 1, I reach C. And from ABC, reading a 0, I'll stay at ABC, and reading a 1, it reaches CD. And still we have this empty set. If you see that once you reach the empty set, you will stay at the empty set. So that's kind of a trap state. Once you reach there, there's no way out. Finally, we define the accept states. For this DFA, the accept states will be a set of states. Each state is going to be a set of states. So each state, each member in this F should contain at least one final state in the NFA. In this case, we only have D as the final state in NFA, so any state that contain this D will be a final state in this DFA. So in this case, we have two final states, CD and D. By double circle them, we denote them as the final state in the diagram. Now this diagram contains all the information for this DFA. The start state is A, the final states are D and CD, and each node is a state in this DFA, and all the transitions define the transition function as a whole. After you construct this machine, you need to count the number of arrows. For each state, the number of arrows out of that state should equal to the alphabet size. That means for each state, on each symbol, I want to know deterministically where will that lead us to. And for safety, you can try some example strings and see if those strings are both accepted by the NFA and DFA or both rejected by the NFA and DFA.